All right, let's talk about the absolute unsung hero inside every single piece of tech you own, the integrated circuit. I mean, this thing is the brain, the powerhouse. It's the tiny, tiny marvel that makes literally everything possible.
No, seriously, just think about it for a second. How in the world does your phone, that little rectangle in your pocket, hold your entire life? Your photos, your connections, all those complex apps. What's the secret? Well, the answer is basically a tiny, impossibly complex city etched onto a sliver of silicon.
Okay, so let's dive right in. We're going to start with the absolute basics. You're going to see how we take a simple element, silicon, which is really just purified sand if you think about it, and turn it into maybe the most sophisticated thing humanity has ever created. So what is an integrated circuit, or an IC? Well, here's the key thing. It's not just one little part. It is a complete circuit. We're talking transistors, resistors, the whole shebang, all shrunk down and perfectly built on one single chip. And that is the secret sauce that makes our electronics so incredibly efficient, so reliable, and of course, so small. But, it wasn't always like this, not even close. The whole story of the chip is really a story of miniaturization. Over the last few decades, we've gotten, well, unbelievably good at cramming more and more power into smaller and smaller spaces. Let's take a look at how this whole thing snowballed.
I mean, the speed of this progress is it's staggering. This is that exponential growth you've probably heard of, Moore's Law, and it has driven everything. Back in the 60s, with small-scale integration, or SSI, you were lucky to get 100 components on a chip. Then we hit medium, then large scale. By the 80s, VLSI gave us the first microprocessors with hundreds of thousands of components. But just look at that jump from then to now.
Yeah, we are now in the era of gigascale integration. We're not talking thousands. We're not even talking millions of components anymore. We are talking billions, billions with a B. Billions of transistors packed onto a single chip, just like the one that's powering whatever device you're watching this on right now. The precision to make these things is it's insane. We're talking features that are smaller than a virus. It's a scale that is genuinely hard to wrap your head around. And this absolute explosion in density, it has some really direct, really powerful consequences. See, fitting more stuff into a tiny space isn't just some cool party trick. It means our devices get smaller, they get faster, they get way more powerful, and this is the kicker, they do it all while using less energy. This right here has been the engine of pretty much all technological progress for the last half-century. Okay, so we've packed billions of these things onto a chip. Great, but what are they all doing in there? To really get that, we have to understand the two basic languages that electronics speak: analog and digital. And trust me, getting this difference is absolutely key to understanding everything else. Here's the easiest way to think about it. An analog signal, that's like a dimmer switch on a light. You can slide it smoothly to any level of brightness you want, right? It's continuous. It's perfect for messy, real-world stuff, like the sound waves coming from my voice right now. Now, a digital signal is totally different. It's just a regular light switch. It's either all the way on or all the way off, a 1 or a 0. There is absolutely no in-between. So let's tackle the analog world first. This is where the chip has to deal with reality. And in this world, there's one main hero component. It's the thing that takes all those messy, real-world signals, sound, light, temperature, and starts to make some sense out of them. And that hero is the operational amplifier, or just op-amp for short. Its job is actually beautifully simple. It just looks at two different inputs, finds the tiniest little difference between them, and then cranks up the volume on that difference. It amplifies it. This is so crucial for taking a weak signal from a microphone or a sensor and making it strong and clear. Honestly, without op-amps, your phone wouldn't be able to hear you. All right, now let's flip over to the digital world. And this, to me, is where things get really fascinating. Because all the amazing, complex stuff your computer does, from just browsing the web to running a super high-end game, it's all built from just a handful of incredibly simple rules. And it all starts with this one concept: binary. Every single thing, every calculation, every decision, every instruction that happens inside that chip gets broken down into a long series of just ones and zeros, on and off, high and low. That's it. That's the entire language. The real magic is in how you combine them. So, how do we actually combine them? We use something called logic gates.
Let's start with the first one, the AND gate. The teamwork analogy here is just perfect. Think of it like a project where, to get a successful outcome, a high output, a 1, every single person on the team has to show up and do their part. In this little chart, the truth table shows it perfectly. Look, the only way you get a 1 on the output is if input A and input B are both 1. If either one of them is a 0, forget it. The output is 0. Simple as that. Okay, next up we have the OR gate. Now this one is a lot more laid back. The best way to think of it is like voting. It doesn't need everyone to agree. It just needs one yes vote. If input A or input B is a 1, then the output is going to be a 1. And you can see it right there in its truth table. The only possible way to get a 0 for an output is if both of the inputs are 0. Any other combination, you're getting a 1. And finally, we have this simplest one of all, the NOT gate. And I love the nickname for this one, the rebel gate. Why? Because it does the exact opposite of whatever you tell it to. It's got just one input and one output, and its job is just to flip the signal.
I mean, look at that truth table. It couldn't be any simpler. If you give it a 0, it gives you back a 1. If you give it a 1, it gives you back a 0. That's it. It's just a digital inverter.
So, get this. With just those 3 simple gates, AND, OR, and NOT, you can literally build any digital logic circuit you can possibly imagine. Every single calculation your computer makes is just a gigantic, incredibly complex combination of those 3 basic ideas. But what if you could make it even simpler? Now here's a really cool thought experiment. Could you actually throw out 2 of those gates? Could you build absolutely everything, the ANDs, the ORs, the NOTs, using just one single type of gate, just repeated over and over again? It sounds kind of impossible, right? But the answer is a definite yes. And this brings us to the amazing concept of a universal gate. It's a special kind of logic gate that's so versatile, you can wire them together in different ways to make them act like any other gate. And this is a huge deal for designing circuits because it makes the whole manufacturing process way, way simpler. And here are the 2 superstars, the NAND gate, which is just an AND gate with a NOT gate tacked on the end, and the NOR gate, which is an OR gate with a NOT on its end. The reason these are so powerful is that you can build everything from just one of them. If you're clever about how you arrange a bunch of NAND gates, you can make them behave like a NOT gate or an AND gate or an OR gate. This is a game changer for chip designers. It means they can build almost unimaginable complexity using just one single repeating Lego brick, basically. And that right there is what's so absolutely mind-blowing about all of this. We started with the simplest rules imaginable, on and off, and an OR. And from that simple foundation, we've built these microscopic cities with billions, literally billions, of tiny inhabitants all working together in perfect sync to power our entire world. It just makes you wonder, as these tiny cities on a chip get even smaller, even denser, even more powerful, what incredible new realities are we about to build next?